All right, so now let us start. Kind of our last topic is Selberg trace formula. There is a very nice paper by McKean. I think it's written in 60s, I suppose, or 17s. So H. McKean. So this he has a very good account of this result. Of course, what we are going to do in this case is the co-compact case. I mean, still a simple version. Okay, so the setting is like this now. M is a closed two-dimensional Riemannian manifold, so oriented. Riemannian manifold. So with constant curvature -1. Constant curvature equal to -1. So these are called hyperbolic manifolds. So closed hyperbolic surfaces. So now, of course, if you apply like Gauss-Bonnet to this, so with this Gauss-Bonnet, remember differential geometry of surfaces. This is, I believe, 1/2 pi integral k the area over your manifold is essentially equal to Euler characteristic of M, right? Which is 2 minus 2g. So this is genus. G is genus, is not the metric. Sorry. So this is the genus. This Euler characteristic is this. So because this guy is negative, it follows that. So this is less than 0. So it follows that the G is bigger than or equal to 2. So then you can use classification of closed oriented surfaces according to their genus. Then you have that this surface is actually topologically is a sphere with G handles. So it's a genus G surface. Genus bigger than equal to 2. So topologically, smoothly, we know this guy. Then what you can do, you can of course look at Laplacian delta, because we have fixed a metric that has constant curvature -1. So you know how to take Laplacian. So this is scalar Laplacian. So then you can take, as we did all the time, you can take it a spectrum. So a spectrum is lambda 0 equal to 0, less than lambda 1, the next one, less than equal to lambda 2, so on. And these guys go to infinity. So these are spectrum. So lambda 0 equal to 0 corresponds to eigenfunction, constant eigenfunction 1, because I'm also implicitly assuming that my surface is connected. So the eigenvalue 0 has multiplicity 1. It's a simple eigenvalue, so this is constant function 1. But higher eigenvalues may have multiplicities. Now, one of the first intriguing things about this constant curvature surfaces is that lambda 1 is always bigger than or equal to a quarter. So this is a fact. I think, well, this is, I believe, due to Selberg himself, but it is proved in the paper again, so maybe you will see that. Fact is that this lambda 1 is bigger than or equal to quarter for any such n. Any such n. Remember, we have this constant curvature -1 assumption. So this is very interesting. It's bounded below. There's a gap always between lambda 0 and the first algebra that cannot be breached. That's interesting. And there are very interesting conjectures also related to this for hyperbolic surfaces, non-compact hyperbolic surfaces. So conjectures about non-compact hyperbolic surfaces. We don't deal with these things, but you can read up stuff. There are interesting conjectures about this related to this fact in general, hyperbolic surfaces. Of course, the spectrum is not discrete. There is a continuous part, so you have to be careful. But that's so. This is a side remark. All right. So we have this now. Okay. Now, what you can do, you can take the universal cover of this. This is the universal cover of M. So this universal cover now is a simply connected, complete Riemannian manifold of constant curvature -1, because when you lift this to the universal cover, the metric, local metric structure doesn't change, so curvature remains the same. So it's constant curvature -1. So this is a simply connected complete to the manifold of constant curvature equal to -1. And as I mentioned several times before, there are these classification results that tells us that this M tilde is, one model for M tilde is upper half plane. Right? So M tilde actually upper half plane, but general classification theorems for such symmetric spaces. So M tilde is upper half plane. There is also disk model, and there are other models for this. And then the metric in this case is Poincare metric, right? So now that's very interesting. So it means that M, any such manifold, any such M is obtained as quotient of this upper half plane by some discrete group of isometries, because the map is a local isometry. So the group that acts is by isometries. So you just get that M is equal to H divided by some gamma. Now this group gamma is a subgroup of orientation preserving isometries of H. And this, we know, this is a general fact from hyperbolic geometry, from classical hyperbolic geometry, as we mentioned several times. This is PSL2R, right? So this is discrete subgroup. So that's the setting now so far. So we have got this discrete subgroup. And in fact, we know what this discrete subgroup is. This is, in fact, nothing but the fundamental group of your manifold, right? So this is gamma is equal to pi1. So let me write it. Pi1 of m. So this is the group of base loops up to homotopy. And it doesn't matter which point you choose on the manifold. So this is, we can just take the point here, like x0, right? And then you can take loops. So you go once around this, once around that, and then once around this, the other one. And then you can go the other way around. Okay, so I cannot quite. So this group gamma then is, as a group, is just generated by 2G generators, A1, AG, B1, BG, with one relation, which is a product of, G is the genus, in this case was 3, product of group commutators of AK, BK, K from 1 to G is equal to 1. So it's a group with 2G generators and one relation. So this group you can compute using a basic pi1 theory. So this is of course AK, BK, AK inverse, BK inverse. I mean this presentation is correct even for G equal to 1, because in that case it just means that your group is abelian generated by 2, so it's a free abelian group of rank 2. This is the 2, and that's the torus case. That's the torus case that we looked at, but here it's much more general. Now, one thing that you can also look, you can just get rid of this phi 0. So this is isomorphic to the group of free loops, free continuous loops in M. So this is basically, I just write it like this, S1 and M. So this is homotopy classes of maps from, continuous maps, of course. So loops, continuous maps from S1 to M. So you can get rid of this initial point and think of it as just loops up to 3 homotopies. So loops that move here up to 3 homotopies. This needs a proof, but this proof is not difficult in this case. Okay. So,
sorry, a question.
Yes.
In this set of homotopy classes, is the group structure concatenation?
Which one here?
The second one, the free loops. The free loops. What is the group structure?
The group structure is again. In this case, you don't see. You don't see the group structure very well. In this case, of course, it's just concatenation. In this case, you see, if you have two such things, if you want to take the product, so you have one map, you go there, and then, I believe it's not very easy to see the group structure in this picture, but in this picture it's very clear, as we know, of course. Yeah.
Oh. Yeah, I'm just wondering because, like, if we wanted to concatenate 2 free loops, we would have to choose a path from one to the other, and the product will not be canonical.
No, but we are going to homotopy classes of maps. You see, this is homotopy classes of maps.
Yes, but if we choose, it's possible because the space is not simply connected. The choice of path from one loop to another will change the
Yes.
homotopy class.
Yes. Yeah, I think you have. Yeah, I think it's not very easy to see it in this picture. You have to write. You have to first make the identification once for all paths, and then.
Okay, so by choosing a base point and by choosing a path from every single homotopy class.
Yes,
okay.
yes. You just make one identification for each class, and then you use this picture. Yeah.
Okay.
Yeah, that's a good comment. Yeah. Right. Okay. So now, so what we want to do, we want to see that there exists now a oh, what am I doing here? Actually, so what I want to say is actually not. I think it's related to your question. What I want to say is that. Oh yeah. No. This is not. Sorry, this is not isomorphic to that. Yes. Yeah. This was yeah. No. I think this is gamma. Now consider this. Now, what I want to say is that actually conjugacy classes of gamma are in one-to-one correspondence with such things. Yeah. But once you do that identification, you have to go back for the other one, and that creates conjugacy classes. Right. So here's a lemma. Yeah. So that's right. Lemma is that conjugacy classes, there exists one-to-one correspondence between conjugacy classes of gamma. So this I denote by gamma, and this S1 and N. Oh yeah. So this is the set of conjugacy classes of gamma. My notation is gamma here. So this is the set of conjugacy classes of gamma, and this is the set of free loops up to homotopy, right? Again, free homotopy classes of loops. So, so what happens, for example, in this picture, the identity, because the identity of the group corresponds to one class, is a single class, it has just identity. This simply corresponds to the constant loops. Now, the constant loop, of course, you can go anywhere, right? You just map S1 to any fixed point. This is constant loop, but they are all homotopic because the space is connected. So that corresponds to one class here, and this corresponds to this. But in general, a non-trivial conjugacy class, right? A non-trivial conjugacy class corresponds to a non-trivial loop here up to homotopy. And how you can do this? Well, you can do this by exactly the procedure that we have been discussing here, actually, in order to write this. Right. So, and in general, you can do the following thing. So let me write a map maybe from right-hand side to left-hand side. So if you have a loop on M, so let's write another picture just here. So imagine you have one loop, for example. It's a closed path on M. What you can do, you just have the universal cover, right? You just go to the universal cover. I mean, lift this to the universal cover. So lift loop universal cover. Okay, so this is your loop. I mean, you have to, first of all, choose an initial point in the universal cover. So this is x0, this is x0 tilde in the universal cover. And then you follow. There's a unique lifting after that. But then when you come back to x0 again, you're not ending at necessarily the same point. You may end up at x1 tilde, for example. But this x0 tilde and x1 tilde, they correspond to the same point. They project to the same point. It means that by the action of your group, you have to go from here to there by some element. So there exists G such that G of x0 tilde is equal to x1 tilde. Okay, now you have made some choices, right? Because there is this point that you choose, and that's after that is fixed, but then there is also, there could be different choices for G, because, but I'm assuming, but the action is transitive, and so there shouldn't be any. Yeah, I think there's a unique G. If x0 tilde and x1 tilde is fixed, there's a unique G. But x0 tilde is not unique. But the choices that involved in choosing x0 tilde means that if you go to the quotient, to the conjugacy class, it's fixed. So just take conjugacy class of G. So this loop now, like alpha t, so send this loop alpha t homotopy to the conjugate class of this. And then you can just sit down and using basic pi1 theory, check that this is one-to-one correspondence. Right. So the idea now is that these conjugacy classes for us is really the analog of the lattice. So that's the philosophy now. So the set of, so I mean, this is not the conclusion. So the idea now is this. Of course, we have to prove, I mean, we have to kind of corroborate this idea. The idea is that the set of conjugacy classes of gamma is the analog of the lattice for the torus. In the torus case. So let us recall what we had in the torus case. Remember, we had this thing, we had this, so now I'm choosing a different notation. So recall we had this gamma inside Rn, a lattice, a co-compact lattice. And remember, we had this Jacobi inversion formula, so let me write it here. So we have this Jacobi inversion formula. So what was this Jacobi inversion formula? It gave us a kind of equality of two traces, exponential of minus 4 pi squared, absolute value of omega prime squared t. So this omega prime belongs to the dual lattice gamma star. This is equal to sum of, so first of all, there was a very important factor, area of M, or volume of M in general, because of this. Okay, let's look at this case. And let's write, because I want to immediately apply, compare to that case. So area of M, yes, divided by 4 pi t, because it's two-dimensional, exactly. Times sum exponential of minus omega squared over 4t. Right. So this is the result that, so now what is omega? Omega belongs to gamma. Okay, so omega belongs to gamma. So let's look at this. First of all, how did we prove it? We derived it in 2 steps. First, we proved this Poisson summation formula, right? Okay, so first, summation formula, which basically said something to the effect that for any f belonging to Shor's class of R2, for example, sum of f of omega prime belonging to gamma star, summing over the dual lattice, is equal to, in general, for any f, that area, something, I believe, area of M, I think, was, I believe this was the formula sum, f of omega belonging to gamma, something like this we had. And then we picked a good function. The good function was Gaussian. So we have this plus, let f be equal to exponential of minus 4 pi squared x squared. It's a two-dimensional Gaussian, right? Gaussian. So that was the way we proved this result. And this result now, what is the importance of this result, as we discussed many times, is that it has 2 sides. One side is related to lengths of vectors in the lattice. This length of vectors in the lattice, this lattice gamma, corresponds to lengths of closed geodesics in the torus, right? This is essentially, this is the geometric side, the right-hand side. This is lengths of closed geodesics. But these guys are, omega prime is basically a spectrum of the Laplacian, right? That's a spectrum of the Laplacian. That's what we saw. So basically then this Jacobi inversion formula, well, in this case, in this form, says that this kind of length spectrum of M, which is R2 over gamma, determines Laplace spectrum and vice versa, right? Because if you know this side, you know this side, and you know all those numbers. Okay, now we want to prove an analog. So Selberg trace formula, as mentioned, is an analog of this result. The analog of this result we have for this p-trace formula. So in general, this PSF is replaced by a p-trace formula. We can say Selberg p-trace formula. So So this is a very general formula. I mean, if you know this by itself, won't tell you anything about the relation between spectrum and lengths. You have to choose your function in a good way, and this is the function we choose. So we are going to play the same game here for this higher genus case. And as I said, one idea now is that this set of conjugacy classes is a replacement for this gamma indeed. So this bracket gamma is a replacement for gamma, for the lattice. Of course, it's not a lattice, it's just a set. It's just a set. But the fact that conjugacy classes appear already was seen in the pre-trace formula. You already saw that, right? So that's the thing. So okay, now so now let's so some formulas of hyperbolic geometry is needed. Okay, I believe, right. So now, so also length of a lattice for an element of the lattice, in this case, gets replaced by, it has a new analog. So there is this length of Q, which is 2 cos hyperbolic inverse of 1/2 trace of Q. So this is a kind of important thing that appears in the formula. So let's see what is that. I mean, first of all, this Q belongs to is a conjugacy class, right? Is a conjugacy class. So what do we mean by length of the conjugacy class? We mean this number. Now I have said trace of Q. By this we mean really a trace of any Q for any Q belonging to Q. So you just pick any element in your conjugacy class and take its trace. Because after all, I mean, this is Q belongs to PSL2R, right? I mean, you can take its trace. So this is the class of A, B, C, D, and you can take to A plus D. If you work with plus minus 1, you have to take absolute value of the trace because you multiply this could be minus A minus D, but then absolute value doesn't change. So Q to absolute value of trace of Q in general. So you can, but this number is well defined, at least in this case, and that's the analog of length for us. I will tell you why this is really length. So now again, this is a formula for hyperbolic geometry. Maybe I can mention this here, is that this is not a difficult fact, is that this number LQ is indeed length of a loop of a minimum distance, minimum length of a loop of minimum length. Yes, that makes sense to say that. Minimum length in Q. I mean, in the the free homotopy class of paths that corresponds to Q in the class that correspond to Q. So what we are saying is that we are saying, okay, so we have got this conjugate class Q. This corresponds to a free homotopy classes of loops, some class of loops. And in this class, you search for the loop with minimum length, basically geodesic in that class. And the length of that geodesic is exactly this number. I mean, this is not very difficult to compute because because we know formulas for lengths of geodesics. Of course, there are no closed geodesics in H. The closed geodesics are all in the quotient, but there are formulas. I will write them down of lengths of like distance, length of this circle, part of circle in the hyperbolic metric. I will that this will justify that formula soon. So that's one piece of philosophy we need. Okay. So any questions or comments? Okay. So now let's, so this is a kind of a little bit of geometric background to this. But now we have to do a little more group theory. So why do we need that? Because we want to understand conjugate classes a little better. I mean, maybe, yeah, I think for proofs at least it is needed. In general, it's a good thing to know. So let me write down this Iwasawa decomposition. So basically, it tells you that SL2R is equal to KAN. So let me write it down. K is the set of all matrices of the form cosine theta, sine theta, minus sine theta, cosine theta. We can just take theta less than less than 2 pi, bigger than equal to 0. These are rotations. It's certainly a subgroup of SL2R, these matrices. And A is the set of all matrices of this form, A, 0, 0, A inverse. You see, the determinant has to be 1. And so you can take A, anything between infinity and bigger than 0. So this is the group of magnifications or scaling groups. Magnification. Subgroup. So if you write this yeah, I mean, these are like 2 by 2 matrices, but these matrices do not act as matrices on upper half plane. They act as Mobius transformations, and these are very, very different things, right? So in this case, this acts like Z2A2Z. So it just magnifies by a square. So it's kind of very simple. This kind of a simple thing to understand. You just magnify any point, you just multiply. And you can see that it sends H to H, of course, and it's. But then N is the set of all things of the form 1. I believe you can put anything like here, B, 0, 1. But B belongs to R. This is also a subgroup here. This is just a group of translations without doing any rotation or inflation. So that sends Z to Z plus P translations. So the Iwasawa decomposition says that actually, I mean, this is something interesting from linear algebra here, you know, for SL2R, at least it's easy to prove that the map from K cross A cross N to SL2R, sending like K, A, N to the matrix K, A, N, is actually a diffeomorphism. But it's not a group map, okay? But by no means this is a group map. It's just a smooth, it's a diffeomorphism. Of course it's not a group map, because as a group, I mean, this left-hand side is an abelian group, but this group is not abelian, right? This is an abelian group. Yeah, this is an abelian group. Translations. I mean, it's a kind of not very interesting group. This is the interesting group, but this is a diffeomorphism. So it means that any SL2R matrix can be uniquely decomposed as product of these three matrices. So this is a good exercise in linear algebra. You can start by Gram-Schmidt, actually. That's linear algebra I'm teaching now. So, or maybe the linear algebra that I'm not teaching now. So Gram-Schmidt process. So proof. So let me write it like this. Proof. Use Gram-Schmidt process. You can prove that. But the point is that this is true of informal generality for semi-simple Lie groups in general. That's true. So now we can now write anything. You can now identify the conjugacy classes here according to trace. So conjugacy classes of SL2R are of three types now. So elements with trace of G, which is A plus B, this is less than 2. You see these elements, trace is 2 cosine of theta. Of course, now let's assume G is different from identity. Because identity has its own single conjugacy class, which is kind of, yeah, it's a very selfish element. It doesn't mingle with anything else. It's just there, nothing else around it. It's just isolated, in some sense, isolated, not really. Okay, now, so first case is that trace of G is, so then G is conjugate to an element in K. So there are those, and of course, if you fix the value of trace, its conjugate class is fixed, because you cannot just have, you know, different traces to be in the same conjugate class, right? So then you pick one theta, you can write it like this if that's the case. The second types are where trace is bigger than 2. Of course, here these are these magnifications, because trace in this case is A A inverse, this is bigger than 2. Again, notice that A cannot be 1. So this is A plus A inverse is strictly bigger than 2. So this is magnification. Then G is conjugate magnification. And of course, the third case is that trace is equal to 2 in that case. And then in that case, it's conjugate to an element. So basically, I mean, by picking different elements here, we have a good picture of these conjugate classes, and in fact, these conjugate classes they are parameterized by the value of the trace essentially. Okay, so now one thing is very important to know, and that's the fact that we have got smooth manifolds. So there are no all isotropic groups are trivial. So let me write it like this. Now, since M, which we obtained as quotient in H by this gamma, remember, is inside SL2R. Yeah, so I should say PSL2R, I guess. And then I have to put absolute value signs here. So sorry about that. So, but that's M equal to that is a smooth. It means that this gamma does not have any torsion elements. Cannot have any torsion elements. In fact, it implies that gamma, gamma has no torsion elements. I believe these groups are called Fuchsian groups. But I don't need this terminology, but these are the ones that studied intensively first by Poincaré. I mean, when he wanted when he wanted to extend results of about elliptic curves and elliptic functions to higher genus things, he had to classify more or less, understand such groups. So. Okay, but now what we want to do is,
Can I ask the question?
Oh yeah, sure.
So what if we have a rotation multiplied by a dilation? Like it's possible to choose them so that the trace is still less than 2.
Well, you can. Not really, because you see, I mean, a trace, I mean, these are really, okay. So you're saying if you multiply 2 of them?
Yeah, like the 45-degree rotation multiplied by a dilation where A is very close to 1 but not 1.
Remember that, of course, I mean, these matrices do not act as matrices on the upper half plane. Oh. they act as Mobius transformations.
Yes, but the product of these two matrices should still have trace less than 2, right?
Yeah. So what matrices you're taking?
The 45-degree rotation.
Well, that
So
one has trace less than 2, yes.
yeah. So its diagonal elements are both 1 over square root 2. I think.
The cosine theta, sine theta I take, right? Minus sine theta and cosine theta in general for some theta. Okay, that's the element you take, and then
and then multiplied by the dilation of, let's say, like 1.1, and the diagonal element is A is equal to 1.1.
Okay, that's fine. Yeah, just take A. So and now you're looking at trace of this guy.
Yeah.
Okay, and then what we are saying about it?
I'm saying that it's the trace should still be, you can choose theta and A so that the trace is less than 2, but it is not conjugate to any element in K.
But why? I mean, if you just multiply this, yeah, I mean, so the trace here, well, let's see. I mean, what is the trace here? I mean, here is A cosine theta, right? Here, right?
Yeah.
A cosine theta, and here is A inverse cosine theta, right?
Mm-hmm.
Okay, so this is 0, 0. So we have got like 2, so this is like A cos theta. This trace is going to be plus A inverse cosine theta. So this is like 2, no, this is like A plus A inverse cosine theta. So now we're saying that, so you want to say, well, I mean, this cosine theta is less than 1, and this is bigger than 2, always.
Yeah, so we can choose theta so that it cancels out the size.
Yeah, so if you choose A is small enough, you can approach to 2, and then I believe you can arrange A to be the whole thing to be less than this. Now, but why you're saying this is not conjugate? I mean, I did not prove this completely. I just gave one direction. I mean, in fact, it is a theorem that this is this is indeed, if its trace is less than 2, then it is conjugate to something in this rotation world.
Okay. I guess my intuition must be wrong. It must be conjugate in some strange way that I did not realize.
Yeah, I mean, maybe, as I said, because we are always thinking of these 2x2 matrices as acting by linear transformations on H, but they are not acting by linear transformations on H. But okay, but that's conjugation in any case is in SL2R, so that's 2x2 matrix. Yeah, I mean, yeah, that's a good thing to try to actually write it conjugate to some element. So I believe you can do this. In this case, this is just a linear algebra, because now I'm teaching this linear algebra. Now so I have to tell my students tomorrow actually about this thing. So okay, so I have to prepare myself. Yes. Okay. Yeah. So yeah, no, I think that's that's a good point, but I think this is okay. Right. So what? So one more formula we need. Okay, we are okay. One more formula. So the formula is this. That's what I alluded to. So imagine you have upper half plane, and so the geodesics, are either straight lines like this, or semicircles that are orthogonal to this line, right? Okay, so there are no closed geodesics on H, of course, but there is a nice formula for the distance, geodesic distance between these two. So this is the hyperbolic distance. I write it like this: distance hyperbolic of x. Maybe I should say z1, z2, because we are in the upper half plane, is equal to cosh inverse of 1 plus Euclidean distance of z1, z2, which is absolute value of z1 minus z2, right? So this guy is just absolute value of z1 minus z2 divided by 2y1, y2. Of course, you're assuming z1 is equal to x1 plus iy1, and z2 is equal to x2 plus iy2. So you divide by these heights, the distance. This is the hyperbolic distance formula. So, okay, so yes. I mean, there is a formula for, yeah. I mean, this is one of the formulas, standard formulas of hyperbolic geometry. I mean, this is very well known formula. I mean, and it was known that instead of trigonometric function, hyperbolic trigonometric functions appear. By the way, in this case, these elements are called hyperbolic elements. These are called hyperbolic elements. These are called parabolic elements. Oh, sorry, these are called the elliptic elements. And these are called parabolic. Also, those subgroups KAN, I mean KAN. Yeah, this is a parabolic subgroup, and this is the part that we are mostly interested in, this hyperbolic elements. So from this, you can also conclude that. So remember, recall we defined length of G, and you can check that this is not very straightforward. Actually, it needs some proof. So I'm not going to do the proof. Length of Gn is equal to n length of G. Actually, this is absolute value of n length of G. So my formula for length, okay, I gave the formula for this, so let me not just, so this is for any n belonging to Z, for any G belonging to Q. Now you see, with respect to this length function, you notice that this is almost behaving, now this is exactly behaving like lengths of those lattice points. Instead of Gn, we have Ng because it was abelian. And if you go Ng, the Euclidean, this metric, it gets multiplied by n. And here also, if you repeat this n times, this length gets multiplied by n. So this is a very important formula for our things. Okay, now we can just write down the trace formula. In the form that we want. Are there any questions? Oh, there is something in the chat, I guess. Okay, so
just working out details of the what we were talking about just now.
Okay. Very good. Thank you. Good. Right. Okay, so now let us write down the trace formula in the form that is kind of, yeah, I mean, really it's the Selberg trace formula. Okay, now the idea is this. So Now, what we have to do, fix function k. So from R positive, I believe, yes, R positive to R, which is smooth and rapid decay. So this is a very general function. So this is a bit like the function that we looked at the case of Poisson summation formula, a general function that we took rapid decay Schwarz class. But in this case, it's enough to pick a function which is defined on R like that. This one, positive real numbers. So now let us define let kh. Using this, you can define khxy. So as I said, this is like analog of the function in PSF as k of the cosine hyperbolic of the distance, hyperbolic distance that I had here of x and y. Okay. So now then let this km of x and y be equal to the averaging of this element over the lattice. I mean over this discrete subgroup gamma h x and gamma y. Gamma belong to. Yeah. So let's look at this first. Remember when we were trying to derive this Poisson summation formula, one approach was that, the relation to heat kernel was that we started with the heat kernel on R or Rn, flat space, that we have a formula. And then we averaged it over the lattice to produce the heat kernel over the quotient space. That was the technique, averaging. Here we are doing the same thing by averaging over this subgroup gamma that defines M as quotient. We are hoping to eventually produce a heat kernel for delta on M. Laplacian on M with respect to constant curvature matrix by choosing K in a suitable form. But from beginning, you don't have to fix K to be appropriate for. So let me comment here later. We choose. So this is not like this is like the analog of F in Poisson summation formula. Later we choose an explicit, a concrete K. So this is in anticipation of what we're going to do soon. But let me write it, a concrete, later we choose a concrete K corresponding to heat kernel for this manifold H and Poincare metric. G, this is the Poincare metric. So this heat kernel has been known. It's much more complicated than heat kernel for. Remember the heat kernel K X Y T for flat space for Rn. It was 4 pi T to the power minus n over 2 exponential of minus x minus y squared over 4t, right? This was the heat kernel for flat space. There is an analog for Hn, that's can be worked out, and we need it. I will write it later on, but right now it's very general. So now this Selberg trace formula is the following result. So this is the term. I mean, yeah. So the result is that, okay, integral Km xx dx over n. Remember, Km is this guy, is equal to area of n times the value of k at 1 plus sum n from 1 to infinity sum, there's a double sum, you know why, a non-conjugate primitive elements P. L of P, L is this quantity that we define, essentially some analog of length, over square root of cos hyperbolic Pn, or length of Pn rather, minus 1. Yeah, these are non-conjugate, different primitive elements. So different conjugacy classes cross, and there's one more term here, which is explicit evaluation of an integral now. Okay, so this is times integral from cos hyperbolic length of Pn, because n and p are fixed now for the internal sum, up to infinity, kb db over root b minus cosh lpn. It's a constant for each p and n. It's a constant. So this integral is 1 over the square root essentially, and it depends what kind of function you have. We can just integrate. There's a rapid decay at infinity, so this is convergent. That's not. So this is the formula. This is the formula. So it is a trace formula in the sense that the formula computes the trace in two ways. Let me tell you what. Why? Well, we have this kernel, right? I mean, so let me give you the idea. Let me go through the proof now. Okay, so this formula is what we need. So I can maybe just give you the idea of proof here. This is something. So idea of proof. So using this kernel, we define an integral operator again on C infinity of m, right? So we just define some operator t from C infinity of m, C infinity of m, right? So which is t of maybe phi of x is equal to integral over m, this kernel, km, x, y, phi of y, d volume of y. I mean, dy. I mean, okay, so let me just write it here. In the formula, this dx, so let me explain what this dx is. This dx is just the volume form or area form for m. I mean, this is the this is coming upstairs. At this upstairs, we know what the area form is. It's just dx dy, I believe, over y squared. That's the area form upstairs. I think I used it before. But anyhow, this descends to an area form. I mean, this notation is not good. This should be here. Okay, this x is variable on m, so Yeah, maybe I just use dz bar over y squared. Maybe I should put dx plus I dy h dx minus maybe 1 over 2i. Anyhow, you know what I'm talking about. So this is this one. So this is the integral operator. I mean, because this guy is rapid decay and all these things, so this is a trace class. And as always, we compute its trace in two ways. This is, of course, from the kernel, right? So now this is, so this operator, so trace of t now is equal to, of course, integral km, as we know, x and x dx over n. So that's this side. And now we have to use this decomposition, the summation, and translation invariance properties of this to decompose this integral over conjugacy classes and compute term by term and see that these things are. So this is equal to now right hand side. So that's the issue. So I have maybe 10 minutes. I don't want to go all the way right hand side. So why? So one idea is that you first isolate the conjugacy class of the identity, because there's one term that corresponds to that, and that's the term that gives you this one. Okay. So I believe I can erase this part. So you can just write this as KH. X, I mean, take gamma equal to 1, x y plus sum over gamma different from identity. So this is the term that, now, if you put x equal to y, because we have to go on the diagonal, so this gives us kh xx. But remember, this was the distance between x and x. This is the hyperbolic distance between x and x. So that's 0. Cos hyperbolic of 0 is 1. So this is k of 1. It's this factor. And it's constant. And of course, we are computing, we're taking integral over m, so this area of m comes. So this term is very easy to understand. So this is what we get by just isolating the conjugacy class of the identity. Okay. Now, now I can erase this part. Now, so like on Monday, we can just write it as, so integral km xx dx, km is the sum over m is equal to, now we just derive that area of m times k1 plus now, okay, right, so we just decompose the gamma over its conjugacy classes and from 1 to infinity, sum k belonging to g over, or gamma, I should say, over centralizer of p in gamma. Oh, there is some p, a non-conjugate primitive element And then we just take some k belonging to gamma over gamma g or p, I would say. And then here, let me write it down. Now, we don't need this now because we're going to drive it soon. So integral over f k of cos hyperbolic of x k en k inverse x. Now this is gamma basically dx. So now how come we could jump all of a sudden from that sum, which is from this to this one? I mean, the reason is this. First of all, what is f? Remember, so f subset of h is a fundamental domain for gamma, right? Is a fundamental domain for gamma because you can always choose lots of different fundamental domains. You just pick one fundamental domain. So integration over n is reduced to integration over f. And in that case, this dx is really, if you go upstairs, this dx is really just volume form or area form with respect to Poincare metric. So that's easy to think. Now, this thing is just decomposing this group into its conjugacy classes, right? So plus decompose gamma into various conjugacy classes. Now, these various conjugacy classes are parameterized by, so this is, so let me just say this gamma p is a centralizer of p. P is an element in the centralizer of p in gamma. So, right, I mean, this is a summation over gamma, different from identity inside this discrete group gamma, and we are summing over different conjugacy classes. Now, in each conjugacy class, we have two choices. One is, because we still have to sum over all elements in the conjugacy class, then you can list those elements as p to the power n, for some primitive element p and some n, for all values of n. So p primitive. And n goes from 1 to infinity. I mean, this basically follows from the fact that you have in this conjugate class a unique representative, which is this geodesic of minimal length, I mean, of three things, and then the powers, and there is nothing else. So, okay, and then, so here gamma, I just wrote it like this. A typical element is, I mean, these are representatives of the form Pn, but then you have to conjugate the different elements. But these different elements, because you have a choice here, you have ambiguity, this is fixed by not in gamma, but in gamma mod gamma p. So this is. So then the next, so this is a bit similar to what we had, you know, for the pre-trace formula, and that's not enough. Now we have to take the next step, right? So then you can analyze this thing. Okay, so maybe I just write here. I can erase, I believe, this part. Not much left, actually. I can just quickly wrap it up. in few minutes, I would say. Yeah, definitely. I don't want to go longer. So, yeah, you can just use translation invariance of the metric to write this as K inverse X. And then just get rid of this Pn K inverse of X. So this is the one. Otherwise, I haven't changed anything.
Sorry, could I clarify something?
Yes.
You write cosh and then bracket with two arguments. What the okay? Do I see it? So you have cosh open bracket X and then a comma. Is
what is it? Where is it?
In the after the integral over the fundamental domain.
Oh, this is the D distance. Yes.
Okay. Okay.
This is exactly copied. Should be copied from here. What I had here.
Okay.
Yeah. That's the way this Km was defined. Remember? Right.
Yeah.
Right. Then the trick is now to decompose now. Okay, so basically, so let me write it down and then I will explain. That's easier. So we are up to here. Now I can just say this is equal to the sum. So now, okay, now. So the internal sum. So this is the internal sum. I mean internal integral. That's what I mean. This one. So let me put it like this: internal integral is equal to, you can write it as sum over k belonging to gamma mod gamma p integral over f Okay, so I don't have to write it again. So let me just write it like this. That's equal to this whole sum, sorry. I don't have to write, I can bypass one step. So that whole sum is equal to the internal sum, I should say, is equal to actually integral over fp, yes, k of cos hyperbolic of d of, I mean, this is again distance of x and x dx, where fp now, so what is fp now? Fp, because remember, once you pick, once you fix p, you have this now fundamental domain fp. So where fp is equal to fundamental domain, or f fundamental domain for this group gamma p, which is the centralizer of p in gamma, using invariance properties. Now, this is fp is obtained by stacking together copies of f under translation. So the picture you should have in mind is this fp. You see, this was the sum, right? Here, I erased. This was, it was a sum over different k's, and each of them is over f. You can translate these things, instead of translating the integrand, you can just change variables and integrate over different copies of it. Stack them together. So this basically, the picture you have in mind is that this is like F, this is like KF, this is K2F, and so on. So you stack together these copies of F moved by K belonging to here. And then you get a fundamental domain for centralizer of P. This is simple group theory now. This is very basic group theory to check this, of course. Saying it is another matter, but once you're told, you can check, right? Now, so this is the one. Then the last step is you have to compute this integral. Now, in the last step, but now look, I mean, this is a very concrete integral. You can compute it. So the trick here is, so this is very interesting by change of variable. So since P is conjugate to a Q, remember we argued that all elements of this discrete subgroup, they have to be hyperbolic elements. So to Q, which is send Z to some parameter, I call it M2 Z. So some magnification. This is the hyperbolic subgroup magnification. Then you can actually compute this. After you do this change of variable, you can compute a fundamental domain in the upper half plane in a very explicit manner. So I can erase this now. So a fundamental domain H for new integral okay, so the new integral, yes, first of all, this is FQ, call it, I mean, Q is of this form, right? Is this transformation, sending Z to Z, so it depends on Q. So let's call it FQ now, which is actually, yes, all the way up to m squared, I believe. Yes, minus infinity. So it's here. So x2 is less than m2, bigger than or equal to 1. So yeah. X1, of course, is now for this this integral, you can using this change of variable, you can write down the integral. So it becomes a very explicit integral. Let me not write it because this you can read it actually in McLean's paper now. You can follow everything in the paper now. So and then you calculate the integral, and so this is equal to integral over FQ of some expression. After you compute this, you get the internal part of this after computing the integral. So this change of variable is very important. This you get, the last factor gets you the last factor in the trace formula. Remember, I had cross some final term, you get last factor. Let me write down what was the last factor. So this was like integral from minus infinity, no, from, no. So the finite integral, yes. Integral from cos hyperbolic, from cosh, length of Pn to infinity, and then Kb dB over just a simple square root of b minus this number, cos hyperbolic length of Pn. You explicitly evaluate the integral, changing that, and we have a formula for this dh, you remember, and then you get this formula. And that gives you the trace formula. So of course, I mean, now the question is, okay, what's the relation between this and the spectrum of the Laplacian? I mean, we have an equality. This case very general, so on and so. So this is a still, I would say, not quite a pre-trace formula, because some interesting calculations has been done. So to get the actual, so I mean, this is really Selberg trace formula. I mean, but so let me write it to get the relation. That's what we want, right? With Laplace spectrum. We have to choose the right K. A good K. So that good K is related to heat kernel for Laplacian on hyperbolic space. So this is related to heat kernel of the Laplacian of the hyperbolic plane. So let me write it here, maybe here. So this is going to be heat kernel H X Y T. So hyperbolic heat kernel. And if you do that, then you will see that on one side, spectrum of the Laplacian appears on this spectral side. Remember, we have this Km. This is H, hyperbolic there, but the Km, we have to compute Km xx dx. This really becomes trace of e to the minus t Laplacian of m, if you choose it in the right way. And the right-hand side, really the lengths of geodesics appear. So, and in this sense, after we do that final step, in this sense, you have a perfect analog, non-abelian analog of Jacobi inversion formula and also Poisson summation formula. So this we will finish on Monday. As I said, this is just now for co-compact case. Selberg actually had it for non-co-compact case, which is more complicated because there are some extra terms here still. They're much more difficult to analyze. And okay, that's that. But now for us, so we are going to say, actually that's what Selberg did. He introduced his zeta function for lengths of geodesics, and he could prove prime geodesic theorem. So it basically tells you how the lengths of closed geodesics will grow, exactly like prime number theorem. And also he gave a much better estimate. In other words, in that case, you can prove Riemann hypothesis for that zeta function, and that's what he did. So on Monday, you're going to now use this result after a quick fix here. We're going to prove both results. Of course, there is also a proof of Boyle's law in that case. I don't think you even get better estimates for Boyle's law from this technique. But Boyle's law, there are more general techniques that I mentioned at the beginning. That's true even for general manifolds, compact manifolds, right? But this is very much a story about hyperbolic spaces and symmetric spaces. Okay, I think I should just finish now.